Module 11, the cardiovascular system. Blood as a connective tissue. It is strange to think of blood as connective tissue, but it is made of cells with an extracellular matrix of plasma. It also has protein fibers. You just don't always see them. That's because they are only activated when the blood needs to clot. These features all meet the criteria for connective tissue. Well, let's talk a bit more about how blood clots. Blood is involved in a process called hemostasis. Hemostasis is the process by which the body stops blood loss. I like to remember this definition by knowing that hemo is a word form for blood and stat refers to staying still. So when we are talking about the blood standing still, I think of hemostasis. Hemostasis has 3 stages that occur in a specific order once blood vessels have been broken: the vasoconstriction stage, the platelet plug stage, and the coagulation stage. It is an ordered process so that the injured area is able to mend itself. Think of how a furniture maker might attach 2 planks of wood together. He first cuts tiny holes to fit dowels in them. He then covers the jointed area with wood glue and slides the 2 pieces together. Finally, he will drive small screws to hold it all in place tightly. With that in mind, let's first look at vasoconstriction. The prefix vaso refers to blood vessels, and the blood vessels are made of vascular tissue. In fact, they are a part of the larger cardiovascular system. Well, vasoconstriction is when a blood vessel shrinks up or constricts. So during an injury of a blood vessel, the smooth muscle tissue that surrounds the vessel quickly contracts at the ruptured spot. This makes the opening in the blood vessel smaller, so less blood is lost. Vasoconstriction is a reflex that occurs locally. With greater injury, greater vasoconstriction occurs. This is the physical part of our wood example. Like the dowels physically hold wood together, the vessel constricting physically causes less blood flow. The next stage of hemostasis is the platelet plug stage. When there is blood vessel damage, a positive feedback mechanism results. The blood platelets swell up and get sticky, adhering to each other as well as the blood vessel. So the platelets kind of form a roadblock, plugging up the torn vessel. Now you can see why this stage is named the way it is. The platelets form a plug to prevent blood leakage. They are the glue of our wood example. Now, how exactly do the platelets stick? Well, when a blood vessel is damaged, collagen fibers on the outer layers of the blood vessel are exposed. This is the only time that blood is exposed to collagen. And platelets bind to collagen, so they will only bind when a blood vessel is injured and collagen fibers are accessible. The binding to collagen creates a stimulus in the platelets to release several chemicals, one of which is thromboxane. Thromboxane is derived from a prostaglandin. This chemical starts in motion several processes that cause other platelets to stick. So plug formation only can happen by the blood's exposure to collagen, and that can occur only when there is a tear on a blood vessel. The plug that is formed is called a thrombus. Now, this process of plug formation is for the most part a good thing. Yet there's one situation where thrombus can occur when the blood vessel is not torn. If a person is experiencing hardening of the arteries, their blood vessel lining is rough and can occasionally cause a trigger of a platelet plug even without a torn blood vessel. In this situation, a thrombus is not a good thing because normal blood flow decreases. The technical term for a heart attack, in fact, is a coronary thrombus. This occurs when a major artery that supplies the heart muscle with blood becomes blocked due to a thrombus. Now you can better understand why people who have a higher risk for heart attacks are encouraged to take a small dose of aspirin each day. Thromboxane is derived from prostaglandins, and aspirin slows down the release of thromboxane, which minimizes a thrombus from forming when the blood vessel is not torn. Sometimes a clot forms in a vein, usually in the legs, and then becomes dislodged and travels through the veins to the heart. When this happens, an embolus, which is another type of clot, can form. If that chunk of clot moves to the vessels in the brain, heart, or lungs, a lot of damage can occur. An embolus is more likely to happen when a person experiences a lack of circulation in the legs for a long period of time. That's why people who travel on airplanes for long distances are encouraged to get up and walk around every few hours so that the blood flows well. Both a thrombus and embolus are more likely to result when regular blood flow is interrupted, so it's important to maintain good circulation. Well, after vasoconstriction and platelet plug formation, the third and final stage of hemostasis is coagulation, and there are 3 stages of blood coagulation. During blood vessel damage, there are certain reactions that happen in the blood. In fact, vessel damage sets off a domino effect of chemical reactions to create a material called prothrombinase. That's the first stage of blood coagulation. Whenever you see a word ending with ASE, you know it's an enzyme. And prothrombinase is an enzyme that works on prothrombin. Prothrombin is made by the liver and released into the blood. Under normal conditions, it's always present in the bloodstream. Prothrombinase works on prothrombin to create an active chemical called thrombin. Now, this is one of the rare exceptions to the ASE rule for enzymes because thrombin is also an enzyme. Well, the creation of thrombin is the second stage of blood coagulation. The third stage occurs when thrombin activates a chemical called fibrinogen. Like prothrombin, fibrinogen is also made by the liver, and this is where the fiber creation in the blood occurs. You see, fibrinogen is a water-soluble protein that has the potential to become a fiber. When activated by thrombin, it changes to fibrin, which is a molecule that's not water-soluble. Thus, it begins to form long fibers woven one way and another to form a blood clot. So to sum up, for blood coagulation, prothrombinase forms as a result of damage to blood vessels and the tissue around it. It will then activate prothrombin, a chemical that's already in the blood, forming thrombin. Then thrombin activates fibrinogen, a chemical that is also already in the blood, forming fibrin. And these are the 3 parts of the coagulation stage. Fibrin is made of long fibrous material formed into a network so that it traps blood cells, platelets, and even plasma inside the vessel. Well, as is often the case, there is more to this story. But first, I need to introduce the term coagulation factors. Coagulation factors are proteins in blood plasma that help initiate the blood coagulation process. Most coagulation factors are created by the liver. They are formed via a long process, but vitamin K is a key element in most coagulation factor formation. An interesting fact about vitamin K is that not only can you get this vitamin from your diet, but the naturally occurring bacteria living in your gut also produce it. The blood coagulation factors are identified by Roman numerals. So now with that under your belt, let's take a closer look at blood coagulation. Remember that it occurs in 3 stages. The first stage produces prothrombinase, the second produces thrombin, and the third produces fibrin. Let's take a closer look at what goes on to produce prothrombinase in the first stage. There are actually 2 pathways to initiate blood coagulation, the extrinsic pathway and the intrinsic pathway. The extrinsic pathway starts when damage to the blood vessel brings material from outside the blood into it. And that's exactly what extrinsic means, outside of. The intrinsic pathway begins blood coagulation without contact by substances outside of the blood. It begins with chemicals already in the blood. At a specific point, these 2 pathways join together, forming what's called the common pathway. Well, when tissues become damaged, lipoproteins and phospholipids are released into the blood. We call this tissue factor. Tissue factor then reacts with calcium ions and a protein found in the blood called factor VII. This produces a larger molecule called the tissue factor factor VII complex. This complex interacts with another protein already found in the blood called factor X. Now, factor X becomes activated. It is now able to take part in the chemical process of coagulation. When it is activated, factor X reacts with factor V, along with phospholipids on the blood platelet membrane, and more calcium ions. This finally produces prothrombinase. Each of these reactions in this pathway has a unique trigger to get them started. Tissue factor triggers the reaction that makes tissue factor factor VII complex. That complex then triggers the reaction to activate factor X, and that begins the common pathway. And finally, activated factor X triggers the reaction to produce prothrombinase. You can see why this is called a reaction cascade, behaving like a cascade of dominoes, one after another. Let's get a little more room so we can see the intrinsic pathway now. We're still in the first step of coagulation stage, producing prothrombin. The intrinsic pathway is another way that the blood coagulation can begin. When collagen from the damaged blood vessel walls contacts factor 12, which is a protein already in the blood, it will activate factor 12. Activated factor 12 will react with factor 11, which is also already in the blood, activating it. With calcium ions, activated factor 11 reacts with factor 9, activating factor 9. Then activated factor 9 reacts with factor 10 to make activated factor 10, reaching the common pathway. So you see how both pathways end in prothrombinase being formed. Now sometimes these two pathways can interact. Tissue factor 7 complex can interact with factor 9. So not only will the extrinsic pathway continue to react along its path, that complex will also react with factor 9 of the intrinsic pathway, starting that cascade too. The details of the other two stages, thankfully, aren't as involved, but I hope you're beginning to appreciate the amazing complexities of the human body, the precise details and finely tuned pathways set in place to keep us alive. Now, once prothrombinase is made, it activates prothrombin, which is already in the bloodstream. This produces the enzyme thrombin at the end of stage 2. And thrombin is what makes the blood clot by activating fibrinogen, again, which is already in the blood, to make fibrin threads. Now, if thrombin is not able to activate fibrinogen, it also can react with factor 8 to make activated factor 8. This chemical helps to stabilize the blood clot. Thrombin also can do another job. It can take part in a positive feedback system. If it comes in contact with factor 5, platelet phospholipids, and calcium ions, it can make prothrombinase to create more thrombin. So this is how thrombin can make more of itself. There are two other positive feedback systems involved in thrombin. It can react with factor 8 plus platelet phospholipids and calcium ions to make activated factor 10 that can make prothrombinase. And it can react with factor 11 to make activated factor 11 that can move down the cascade of the intrinsic pathway to make more prothrombinase. Well, that's the blood coagulation process. It has two cascades or pathways of reactions to ultimately produce prothrombinase, then thrombin, then fibrin. Why is this process so convoluted? Well, if you think about it, all these pathways have spots where one material is made and then it has to react with another material to keep the process going. Each spot in this pathway is a point of regulation. Everywhere you see a black arrow, that's another regulation point. That means that these pathways can be carefully controlled so that clots don't just randomly happen. You know that would be a bad thing, right? Thus, clots only occur at sites of vessel damage. And yet, sometimes those sites don't even need clots. They can do with only platelet plug formation or even just vascular constriction. So there are several spots on all of these pathways to carefully regulate the process. Now, there's one more point to address about this process. Your blood has to coagulate pretty quickly so that you don't lose too much of it. The coagulation process has to turn off rapidly too so that all of your blood doesn't clot. So how does this happen? Well, it has to do with anticoagulants. The body makes these special chemicals that prevent certain blood factors from becoming activated. Anticoagulants stop the coagulation pathways at specific steps and thus stop the process of coagulation altogether.